We're going to do an example problem using the technique from section 2.4, graphical convolution. What graphical convolution does is it allows us to perform a convolution more efficiently by looking at the active areas and the different regions of a function, and it helps us avoid some of the complexities of dealing with unit step functions and ramp functions and their domains by handling that part graphically, and then that will simplify the integration that we need to do, so the calculus we need to do gets a bit simpler. So for our example, I'll give us an input x and an impulse response h, but I'll do this in a bit of a different form. So here we'll have x of t. It's going to be 3 minus t in the range t is between 0 and 3. And it's going to be understood that it's 0 everywhere else. I could write that out explicitly, but I'm not going to here. So let's sketch that function out. Here we have a set of axes, and we have 3 seconds, voltage of 3. And if we draw that out, we have this line right here. So that's the definition from 0 to 3. And then outside of that, the function has value 0. And this is the t-axis. So that is our first function. Now we could write that, if we wanted to use the technique we have up until now, we could write it as moving along from left to right here, unit step of t minus ramp of t plus ramp of t minus 3. So we could write it in 3 parts like that, and that would allow us to do the convolution integral, but we would get a very complicated expression because we would have to potentially transform that entire signal x with the 3 pieces, and we would have to multiply them by corresponding components in the impulse response. So we're going to use a slightly different technique with graphical convolution to get to the same answer, but with a little less work and complication. Similarly, I'm going to define an impulse response here as 2 minus t, and we'll have that be a similar function going from 0 to 2. So it's going to look like this right here on the graph. So that blue graph, h of t, remember, is showing us what happens if I excite the system with just an impulse. So if I excite the system with 1 volt second compressed into an infinitesimally small amount of time, so very high voltage over a very small amount of time, the output will be that. But instead, I'm actually giving a more realistic input here, which is a finite voltage of 3 linearly decaying to be 0 volts at 3 seconds. And we can use convolution to determine the output y of t. From our previous lecture, you do the integral of x of the delay variable tau and h mirrored about the new time axis of integration and shifted to the right by t, the independent variable. You do this integral d tau. In general, this integral is from minus infinity to infinity, but we can often make simplifications. For example, here, if we were to use this form of the integral, we see the function x of t, it only has non-zero values from 0 to 3. So we could make that those limits 0 to 3 instead of minus infinity to infinity, because x of tau is going to be 0 outside that range. As your book shows, we can do a variable substitution. We can substitute in the variable t minus tau as an auxiliary variable, and we'll rename that variable t. And if we do that, and we carry through the substitution, what we'll end up with, and I'm skipping the derivation here, is with that substitution, our argument to the x function becomes t minus tau, and we end up with d tau there. So you're substituting in The auxiliary variable, which in the end is going to get renamed to t, is going to be this original t minus tau. And then we do the derivative of that of the tau variable, which will be negative because of the sign here. And then we substitute in similarly here. We go through a bit of algebra, and we end up with flipping limits of integration, and the whole derivation is in the book, and you end up with this integral. This integral shows us that convolution is a commutative operation. So if we have the function x of t and we do this convolution operation with the impulse response h of t, we use this star operator to denote convolution, and the order, it turns out, does not matter. So even though we derived it from linear time invariant system principles in the first form, the second form is equivalent. So this gives you a computation technique. You get to choose whichever integral form is easier. Now, in this particular case, the functions are very similar in structure, so neither is significantly easier than the other. I am going to choose the second form for this problem, but it really doesn't change the difficulty much. If one of your functions, your x or your h, is very complicated, you might want to avoid having that be the one that goes through this flipping and shifting transformation. So if your input x is a very complicated function, and more complicated than your h, you would use this first form, because here you avoid the need to transform the x function. So you take the more complicated function and you say that's going to be the one, x or h, that I don't transform. Oh, and I am going to correct an error here. In the second form, I wrote a t instead of tau. So let's go ahead and fix that. This should be tau. Okay, so now we have our form. Let's take a look at what this form looks like along the tau axis. So tau is the delay axis, and we're going to talk more about what that means. And let's draw out the corresponding functions here. So we're using the second form, so the h function is not moving at all. So the h function, I just make it a function of tau instead of t, and it's that line there. To make the diagram a little cleaner, I am going to avoid drawing out the portions that are 0. Then we have the transformed x function. So first thing we do is we take x and we mirror it, because there's a negative tau in there. So if I mirror it, I will end up with this function right here, starting at time tau is -3 and rising. So I've mirrored the function x of t about the axis, and here I have x of t minus tau, and in this case t is 0 because I have not shifted it. Now if I let t go up to be, say, 1.5, then I have shifted it to the right 1.5 seconds. So this shift right here is the shift t. And I can shift it farther yet. Maybe I shift it 4 seconds, and then I have this function right here shifted 4 seconds to the right. So t is the shift there. Now, usually, if I'm shifting something to the right, we think of that parameter as being subtracted. But here we've mirrored the tau axis, so it works in reverse. So if I say x of 4 minus tau, it's that rising triangle that is farthest to the right. The reason we're looking at this is because it's going to help us simplify the integrals that we need to perform. So let's go ahead and actually calculate the integral now. And let's look at the various regions that it's going to have. So the first region we have is when the shift variable is less than 0. So here we have the value when t, the shift variable, is 0, and if we let that variable go negative, then the transformed input x is moving farther to the left. So when I multiply the orange function, which slides to the left, by the blue function, there is no overlap, and when I integrate it, I will get 0. So in that range, I'm going to have 0 when t is less than or up to being equal to 0. And that's what we would expect from our input functions, because the impulse response starts at 0, which means the outputs occur starting 0, 1, 2, 3 seconds, 0, 1, and up to 2 seconds after the input as we go along this line here. So I think of the parameter here as a delay from the input to the output. And x of t is starting at 0, so there's no way I can get an output before time is 0, and the convolution integral is correctly showing us that. The next region that we have to consider is when the variable t goes from 0 to 2. In that case, this orange function is in this range here. It's illustrated at t is 1.5. Notice when I do this, the function is overlapping from tau is 0 to tau is up to, in this case, 1.5, whatever t is. So I have this moving orange line that is dependent on what the time t is, and I integrate over tau. Now, as this is happening, think of tau as the delay. And when we do this integral, we're saying, well, what is the output at time t based on the contribution of all the different delays between input and output? So look specifically at this one right here. This has been drawn for t equals 1.5. So we have the t equals 1.5 argument right here for the input x. And in blue, we have the h function. So the convolution integral says multiply them together and integrate over the tau axis. So what's happening is we're saying we are dependent on inputs that happened at time 0. And the 0 was 1.5 seconds before the current time t. So it lines up with the blue function, which is a delay of 1.5 from input to output. So this value here multiplied by this value here gives a contribution for what the input x was at 0. Now, as I go 1 second into the future, so I had the input occurred at 1 second. On the transformed function, I go down 1 second here. So now I'm at tau of 0.5 on the axis. So now this is the input right here that occurred at 1 second, and I have a delay on the tau axis of ½ a second. So you add up, the input occurred at not 0 but at 1 second, so I'm over here, and then there was a delay of ½ a second. So in all cases, the time that the input occurred plus the delay gets me to 1.5, because that is the t. So I'm looking at what happens to the function at 1.5. That's what this graph is showing me. The orange graph here, the blue graph here, is showing me all the contributions to the signal at the variable t is 1.5. So from the point of view of this graph, t is a constant because we're following the integral, which says, look at all the different delays, tau, and that's what this axis represents, is delay. So this integral in this range will always go from 0 to t, because the blue function starts at 0. The orange function is starting before 0, but there's no overlap until the blue function is on. Now the blue function is on until 2, but in this range, t can be less than 2, and that's where the range of overlap is going to occur. So we're going to work that as a side problem to figure out what happens in that integral. So that integral is going to be the transformed x times the transformed h. We're going to work that as a side problem, and we'll come back and fill that value in later. But let's look at the other two regions. The next region is going to be when t goes from 2 up until 3. So when t is going from 2 to 3, I have now this edge here will be at 2 to 3, so it's going to be beyond the right edge of the blue function, but the left edge will not be pulled into positive tau yet. When t is between 2 and 3, I go back 3 seconds because that's how wide the x function is. So here, when I'm between 2 and 3, I go back 3 seconds, and it's going to start somewhere between -1 and 0. So in this case, when t is between 2 and 3, so this right edge here has moved over to 2 and 3, you're using all of the impulse response, the blue function, all of it is covered from 0 to 2. So the integral in that case is going to go from 0 to 2 of the x times the h function. And we're going to evaluate that as a side problem, and let's look at the remaining regions. So this, if we were working this out in terms of unit steps and ramps, it would be much more complicated than this approach is. So that's why we're doing the graphical approach. It's actually the simplest way to do it. So now we'll continue on, and we'll have the region such as where we're at 4 here. We're actually going to consider the region where I have just the right tail of the orange function is overlapping the blue function. So that's going to start happening when t is greater than 3. So when t is greater than 3, then the edge of the orange function is pulled off, and I'm going to have some overlap until t gets up to 5, because if it ends at 5, then it starts at 2 because it's 3 wide and it's going back this way. So when t goes up to 5, I will be in this partial overlap region where the blue function ends at 2, but the left end of the input function x is left of that 2. And where is it? Well, this one's a little more complicated, but t takes us to this right edge. So the left edge is going to be 3 earlier for this segment. So it'll be at t minus 3. And then I'm going to have the same argument in all 3 of these integrals. It's going to be the function x times the function h. And finally, I have a 5th segment. Let's write it out. And that is when t is greater than 5. And in that case, my output is going to be 0 because the orange function no longer overlaps the blue function. What does that mean in physical terms? Well, the input x was only on at all from 0 to 3 seconds. So the last input came at 3 seconds. The impulse response says you have outputs occurring up to 2 seconds after the input occurred. So I add the 3 to the 2 and I get to 5, and if I'm beyond that, the output will no longer occur. Now, we need to evaluate these integrals, and what we're going to do is we're going to do it in this general form. All the integrals go from a lower limit to an upper limit. So we're going to call the lower and the upper limit a and b. And then we have x of t minus tau, and we have h of tau. Integrate over tau. Now, we have chosen the limits carefully by doing the graphical approach such that both x and h are in their active areas. So this is where we get the simplification. We don't need the unit steps to constrict the domain of where these functions turn on, because we've already guaranteed the functions are on over on the left-hand side by choosing the upper and lower limits correctly. So for x, you get to write the equation of the line x. And I'm going to write it, and then we'll talk about where it came from. It's tau plus 3 minus t. So if I look at the line for x here, it is a line, has slope 1 going up in the tau direction, so that's the tau term, and it has y-intercept of 3 minus t. So when t is 0, the y-intercept is right here at 3. When t goes to 1.5, the y-intercept comes down to 1.5. As t goes higher and higher, that y-intercept goes down. So if I want to know what this line segment is at t is 4, I have to take 3 minus 4. The y-intercept is minus 1 there. So that is the slope, point slope, slope-intercept form of the equation. Now, I do the same for h of t. H of t is going to be 2 minus tau, because tau is the variable of integration on my axis. So there we have that. We multiply this out, and we get 2 tau plus 6 minus 2t minus tau squared minus 3 tau plus t tau d tau. And now we collect terms. Notice that the variable we're integrating with respect to is tau. So we collect the terms in descending power of tau. So a to b. If I look at the tau squared terms, I just have 1, so I have a minus tau squared. If I look at the terms that are tau to the first power, I have a 2 tau minus a 3 tau. So I'm going to have minus 1. And then I have a t times tau, so that's right there. So I'm getting this in terms of a polynomial with variable tau, and coefficients are based on the parameter t, which I'm treating as constant right now. And finally, I have the items that do not vary as tau varies, so that's the constant 6, and it's the constant minus 2t. So I have plus the constant 6 minus 2t, and I integrate that with respect to tau. So I get the indefinite integral minus tau cubed over 3 plus the constant t minus 1 over 2 tau squared, and then I integrate the constant term with respect to tau, so I have 6 minus 2t tau, and I integrate that from, the limits are going from tau is a to b. So I substitute in the a and the b, the lower and the upper limits. So I'm going to do one of these here on the slide, and then I'm going to leave the rest to the MATLAB code and the corresponding PDF that I'm going to post on Canvas, which is going to complete all the algebra and do graphs of the output and have some additional discussion. So when you're done with this lecture, to complete it, to see the work completed, I'm going to encourage you to do that. It's going to complete all the algebra for us automatically in MATLAB. If you prefer using another tool like MathCAD, you can certainly do it in there, but take a look at the MATLAB result, please. Okay, so let's just do most of the work on the first one. I'm doing the integral from 0 to t, so I want this integral where I go from 0 to t, which is going to be this form right here, evaluated at t, evaluated at b is equal to t, and then subtract evaluated at the value of tau is going to be 0. So the term tau of 0, since there's a tau in every one here, we'll just be subtracting away 0. So what am I left with? I am just substituting in the upper limit b which is equal to t. So all my taus become t's in this expression, and I get minus t cubed over 3 plus t minus 1 over 2 t squared, because that tau is becoming t, plus 6 minus 2t times tau, which becomes t. And we do some further simplification and collect like terms there. We can see there's minus t cubed over 3, and here I have plus t cubed over 2. So we would go through and collect like terms and go through the algebra. We would go through similar substitutions for upper limit of 2 and lower limit is 0, subtract, simplify, and then here the tau becomes 2 at the upper limit, t minus 3 at the lower limit, and we do a lot of algebra and simplify. So what I want to note is very quickly, these simple functions of a line, these first order polynomials, get us to some complicated functions. We have a first order polynomial. We have a first order polynomial here that is multiplied by another first order polynomial. So the degrees add together, we end up with something that is quadratic, or it has a square term, but then we integrate it and we end up with something that's cubic. So with some very simple functions, it can get complicated very quickly. This graphical technique saves us from the need to additionally deal with all the complexities explicitly of where the unit steps and the unit ramps overlap, because we're handling what is the proper domain of overlap and integration graphically. So go to the MATLAB video, the MATLAB code and PDF next. And then your book has some different examples in section 2.4 besides the one we've done here. So please take a look at those as well.